Finite element model of impressed currents in human tissue using QuickField. QuickField is a finite element program that computes time-dependent analysis of current, voltage, and field parameters within a selected geometry. This study was performed by summer intern Meredith Venerus and supported technically by B.E.E.S. The purpose of the B.E.E.S organization is to promote, foster, and advance the development of engineering models that predict the interaction of energy fields in living tissue. Electric currents in the small milliamp or microamp range applied to the body are known to promote healing of bones, traumatized tissue, and wounds. Also, several types of chronic pain can be treated by application of microcurrents. For the healing of bones, both direct currents, interrupted direct current, and alternation currents have been used. For pain mitigation, the more common uses is a pulse DC current of specific frequency dependent upon the type and location of injury. It is also common to use two different signals simultaneously. Such a setup is shown in the next slide. This photo shows a commonly used FSM power supply that the operator adjusts to apply a current of fixed amplitude. This is typically 10 to 100 microamps and chosen frequency for a specific duration. This diagram on the right shows the placement of two electrodes on a patient. The basic issue with FSM and the reason for this study is the absence of any knowledge about how applied currents are distributed in the body. As a result, there is little understanding of the optimum electrode placement or required currents. Before a finite element model can be constructed, it is necessary to have an electrical analog of the body system. As a starting point, we have chosen a very simple model, but one that has considerable foundation in electrochemistry and has been used in other studies. Applied currents are carried in the body by ion transport rather than by electron flow. Except at very high frequencies, the behavior of ion migration in solutions can be represented as a simple resistance. The skin is modeled as a parallel resistance and capacitance. Values of skin resistance in the literature vary from about 10,000 ohms to 10 to the 6 ohms. The parallel capacitance is measured as roughly 0.01 microfarads. For the finite element QuickField model, these values must be expressed in usual scientific units. This chart provides a visual link between the placement of electrodes in a real situation and our simplified two-dimensional model. As you can see, the stick figure represents a patient with the electrodes attached on the leg. The image at the top is a 3D cross-section. The in-view on the right indicates the skin, tissue, and bone. To make it two-dimensional, we use a rectangular diagram as seen on the bottom. On the far left, electrodes are applied to the rectangular model. This model is the basis for our two-dimensional QuickField model, which you will then see coming up next. So today we are going to be using QuickField to model frequency-specific microcurrent as it is applied to a tissue, bone, and skin sample. We will start off by going to the File button and creating a new problem. Our problem file name will be 8243. 824 is just the date, and 3 is the trial number we are on today. This is just for our own record keeping so that we know which problem is which. I'm going to go up to the problem type bar. Transient electric, that is the type of problem we'll be running today. Our length units will be in centimeters, and our depth in the z direction will be 1 centimeter. This is for our calculations. Hit next. We determined that the best timestamp for us 6875. So our be calculated up to 0.06875 in seconds, and our step size will be 0.00025. It's very small. Now we are at our geometric model. Widen that. This right here is the zoom to fit button. You can use this to zero around the origin, and also if your model, you start inserting shapes that are a little big, you can push this and it'll zoom your screen to fit your entire model right on the screen. So we'll start off by inserting a shape. This is the insert shape button. You can choose from rectangles, ellipses, and circles. Today we're going to be using the rectangle option. You can alter the position around which the shape is inserted, but we are just going to use it at the origin today. So the width of our rectangle will have to be 20 centimeters, and the height will be 5. Insert that. You can see that right now you can't actually see the rectangle, but once we're done inserting all of our shapes, we'll hit the zoom to fit button and we will be able to see everything. We're going to insert one more rectangle, and it will have a height of 5.4. I'll tell you in a second why we need to add the 0.4. Insert that as well, and close this box because we're done with that for now. So now we're going to go up to our lovely zoom to fit button, and this is our double rectangle. So when we made the height of the second rectangle 5.4, it added 2 millimeters on either side of the box. This is good because our skin in our model is going to be 2 millimeters thick. So we're going to need this layer. This layer, however, is extra. So we're just going to select it and delete. Yes. Alright, now we are going to insert our electrodes. This is the insert wand. So you use that to draw new shapes if you don't want to use the insert shape button. So we're going to start at this red point here so that all of our vertices are connected. We're going to go up 1 centimeter. And then over 2 centimeters, then down again. Be very careful, we don't want it to end too far down. As you can see right here, this is a little extra. This is going to separate this, which is supposed to be 1 layer of skin, into 2. So to prevent that from happening, we're just going to select it and delete. Also delete this extra vertex because we don't need it. So now this is our first electrode right here. What we're going to do, we're going to select the electrode, go down to the duplicate selection option. So what this function does, it'll duplicate this box, and then we can choose to have it move to any other point in the model. So for today we're going to have it moved 18 centimeters to the right. This is the X direction. This is the Y, so we want it to the right, so X direction, positive 18 centimeters. It'll end up right here on the edge. Okay. And now we have our 2 electrodes. Next, we're going to use the insert shape button again. I'm going to insert a shape with a width of 2 centimeters and a height of 1. And close that. This will be our first bone fragment. In order to ensure that all the bone fragments are the same, we're going to do the same duplicate selection option, except we're going to this time move 1 to the left 6 centimeters, so we'll end up somewhere over here. Now we have 2. I'm going to duplicate this again, and then just get rid of this negative sign, and we'll move to the right 6 centimeters. And this is our geometry model, which we will be using today. First things first, we have to add our labels to everything. So we're going to start with the block labels. Tissue gets a block label. Then these 3 boxes all get a bone block label. And we can select the skin, give it a skin label, and our electrodes as well. So our block labels are done. Now we're going to add our edge labels. Just label this 1, because this is electrode 1. Label this 1 as well. Label this 2, because it is electrode 2. Now that we have all of our labels, we can go in and start to assign values. For bone, because bone is not very conductive, we don't want to set the permittivity or the conductivity to anything. So we're just going to keep this at 1, at none. And as you see, there's a little exclamation point. That's fine, as long as the program knows that that's what you want the bone parameters to be set to. Now we're going to move to the electrode. Our permittivity here will be 1. Our conductivity will be 100 siemens per meter. This is just because of our calculations. For our skin, our permittivity will be 10,000. And our conductivity will be 0.0004. These were values that we determined were most representative of skin's electrical properties when using FSM treatment. Tissue will have a permittivity of 1 and a conductivity of 0.5 siemens per meter. Once again, these were parameters that we discovered were most representative of tissue's properties when using FSM. Our edge labels now we're going to use for electrode 1 right here. Our edge label will be a function. We're going to insert a square wave function. So the function looks like this. The sine function is how you insert a square wave. The 360 times t, because QuickField uses degrees instead of radians, we have to multiply our time by 360 degrees, and then we also want 40 hertz. Okay. Edge labels for electrode 2. We're going to use this electrode to be our ground electrode, so we'll set the voltage to 0. And now we are done with our parameter assignments, so we can go now to mesh our model. This is the build mesh button right here. Select that. It meshes the entire model. If you make a mistake or you discover something before you solve your problem, you can click the unmesh button. It goes right away. For now, we're going to mesh. We're going to move up here to the problem tab, and then right here, solve 824.3. That's our problem. So you're going to select this, solve. Select yes. And now it's going to take some time for the program to solve this just because of the number of nodes. So we'll come back in a second when it's done and look at our results. So it took about 160 seconds to solve this problem. This window pops up. We would love to see our results, so we select yes. And this is the post-processing photo. It's a little boring, so we're going to go right up here to the View tab and select Field Picture Properties. This allows us to view color maps. For our experiment, we usually just look at the potential map and the current density map. So the potential map is this. This is the legend. It allows you to see the highest point, or in this case the lowest point of voltage. which is 19.3. That's good. That's the right order of magnitude and right in the range of actual voltage measurements that we take off of patients. So that was very, very exciting. We can also use this button, which is our local value button. We can select any point within the model and see the voltage change, the field gradient, the current density. It has the coordinates right here. What this allows us to see is that voltage is very uniform throughout the whole model, even in the skin layer, with the highest point being within the actual electrode and the lowest point being in the ground electrode. We can also view time plots. Right now you don't see very much of anything because of the point. But if we add this point, let's see, we'll add this point. So to add a point to the time plot chart, select it, open the time plot. It's a nice curved. This is what we want. If you wanted to add a different point, you type in the point coordinates right here and select add, and it'll pop up again. You see here there's a green line, which was from one of our coordinates, and then the purple line curve is a different set of coordinates. So this line is from I left the cursor in here when I selected time plot, so it was just reading from here because it's zero voltage, it has 0 across the board. But if you select it in a different part, a different non-zero part of the model, it'll come up with this lovely graph. We can also view a timetable. First we have to exit out of that timetable. And just like the graph, we can change whatever point we would like, and it shows over the entire span of time the potential, the electric field, in the x and y direction, and most of the current density and the other values that we are interested in for our research. We also like to view the current density. However, as you see here, the maximum is a very big number, so when we push OK, the current density chart's going to be a little bit boring. So in order to change that, we will go back up to view into our field picture properties and make our maximum 1 amp per meter squared. And we find that this is a bit more representative of what's actually going on. As you can see, it makes everything a little bit more interesting. You can see the high volume of density right around the bone fragments, near the electrodes. We can view the graph of this as well. So if we go to time plot, it'll give us the graph. It looks like we have 3 points here. So it has the current density in scalar and in the x and y direction, so we can get rid of that to make it a little easier to look at. So that about wraps it up for today. This is what we have been using QuickField for our project of frequency-specific microcurrent. We've been able to view the voltage and current density at any point within the model, and has also allowed us to determine values for skin, tissue, bone, and our electrodes, which have been extremely useful. So thank you very much. The results of this beginning 2D analysis already show surprising results. For instance, the current and voltage are distributed rather evenly in the tissue. So the current and voltage flux at a particular site of injury are much lower than might be expected. The next steps are a further parameter study in 2 dimensions, followed by a more sophisticated model in 3 dimensions.